University of Canterbury in Christchurch. So I just learned Ian has a very interesting trajectory into physics. So he graduated from MIT Surat as an undergrad in mechanical engineering before I graduated as an undergrad. And before Raghu graduated as an undergrad. And then he went on to do a master's.
Yes.
In Philadelphia.
In Philadelphia, yeah.
In Philadelphia in mechanical engineering.
Yeah.
Then he moved to industry, but then he loves physics so much that he came back, or he didn't come back, he actually made his entry into physics, did a master's in University of Waterloo, and now he's doing his PhD in astrophysics and astroparticle physics at Christchurch. So he will now treat us to stellar and overlooking and tidal disruptions and so on. Alright, take it away. Thanks.
Okay. Hello everybody, my name is Ian DSouza. I'm a PhD student at the University of Canterbury, so I don't have that over here. But I'm doing a PhD under the supervision of Dr. Chris Gordon and also collaborating with Dr. John Forbes. And today my talk is titled Disruption of Dark Matter Minihalos by Successive Stellar Encounters. And I have a publication on it and also a preprint on archive, 2 papers. Okay, now to just give you a very general background, quantum chromodynamics, which I'll abbreviate as QCD, is the theory of how the building blocks of protons and neutrons interact with each other. Now, according to the QCD theory, it predicts that the neutron should have a large electric dipole moment. However, in practice, we observe that the electric dipole moment of the neutron is actually quite small. Now, axions were these hypothetical particles introduced into the theory. Firstly, the QCD theory has a CP violating term which predicts a large dipole moment for the neutron, but the axions which are introduced into the theory effectively nullify the CP violating term and thereby theoretically predict a small electric dipole moment for the neutron. A little detour into dark matter. Now, we expect dark matter to be made out of particles. It has a particle nature. Now, from observational data, we expect dark matter particles to move significantly slower than the speed of light. So, we call it cold dark matter. And these dark matter particles interact very weakly with normal matter and radiation. Their primary interaction comes through gravitational effects. Now, the QCD axions are one candidate for dark matter, and the axions that I study are have mass of the order of 1 microelectron volt. And I primarily studied the gravitational aspects of clumps of dark matter called axion minihalos. Now, on cosmological timescales, the universe was initially radiation dominated, and then it transitioned to being matter dominated. And during this transition phase called the epoch of matter radiation equality, isocurvature axion density fluctuations decoupled from the Hubble flow, which is the uniform expansion of the universe in space, and they collapsed to form gravitationally virialized structures called the axion minihalo. Now, these primordial axion minihalos, which initially form through spherical collapse, have a power law density profile, but they undergo hierarchical merging to give rise to larger axion minihalos. And we are interested in axion minihalos because they affect the chances for direct dark matter detection experiments here on Earth. Now, these hierarchically merged minihalos, these are the larger minihalos, through simulations, they are predicted to have a spherically symmetric density profile called the Navarro-Frank-White profile, which I'll abbreviate as NFW, and we model it to be so in my research. And the NFW profile is given by this density profile. So, rho is the density and r is the radius. Rho sub s is the scale density. So, this is a 2-parameter model. So, rho sub s is the scale density and r sub s is the scale radius. Now, for the purposes of my analytical calculations, I ascribe a single parameter called the concentration parameter, which I'll abbreviate as C, and it is defined as the ratio of the virial radius of the minihalo to the scale radius of the minihalo R sub S.
Could you go back one slide? Yeah. So why do these density fluctuations form minihalos only during matter radiation equality?
I'm not 100% sure about that, but there are equations that predict so there's a term called delta, which is kind of like the overdensity, the local overdensity, and when you set delta equals 0, it it happens at the matter radiation equality, and only after matter radiation equality does delta become greater than 0. And you need overdensities for spherical collapse.
So this is only for this axions, or this is for?
These ones are for axions, and they're for the isocurvature perturbations. There are also adiabatic perturbations, which I'll come to a little later.
But in general, when you have these isocurvature overdensities, not just to axions, for the entire model, I think they should just happen.
They should, but for the axion, I think for the axions, they happen around the matter radiation equality, as far as I know. But you are right. I mean, they can be overdensities in other particle species as well, and due to gravitational instability, they can collapse to form very large structures.
So what is the minimum mass of the subhalos that this scenario can actually find?
The minimum mass?
Yeah, so the minimum mass of subhalo that we see with this axion dark matter, what is that?
Okay, so initially when they do form through spherical collapse, we sometimes call them axion mini clusters, and those are of relatively small masses, and we don't observe them today because those mini clusters undergo hierarchical merging, and they give rise to larger axion minihalos. But those larger axion minihalos that we consider, that we can potentially observe today, we assume them to have around 10 power, at least 10 power minus 12 solar masses. Okay, so my work mainly looks at the models of mass loss occurring in minihalos when a minihalo encounters a star or comes under the gravitational influence of a star. And I primarily do analytical calculations. Now, there was a paper by Kavanagh et al., which I'll abbreviate as K 2021, that proposed an analytical model of mass loss, wherein they integrated the phase space distribution of axions in the minihalo to compute the mass loss during a stellar encounter. And we proposed two significant improvements to this model. One is the sequential stripping model. We call it the sequential stripping model, wherein we assume that outer shells are stripped off before an inner shell is stripped off. Mathematically, what this does is it more accurately predicts the gravitational potential of each axion. The second improvement we did was post-stellar interaction. We assumed the remnant minihalo to relax not to another NFW profile minihalo, but to what's known as a Hernquist density profile minihalo. And the Hernquist density profile is given by this equation right here. It's very similar in analytical form to the NFW profile, but the Hernquist density profile has a power of 3 here, whereas the NFW profile had a power of 2. Okay, so these ones were more dealing with axions in specific. These were n-body simulations, but they did not, so each body of the n-body actually was not a single particle, but a clump of particles, to make the simulation more tractable. And they did this n-body simulations where they subjected to the minihalo to some energy injection and saw how it relaxes, and they found that after the relaxation, it actually relaxes to what's known as a broken power law, which is where the broken power law might have a different value of, instead of 3, it might have some 3.2 or something like that, but it's very close to the Hernquist profile. I think yes, within the simulation, yeah. But to actually have the minihalo in the first place, we needed to be of axion nature because it's these isocurvature perturbations specific to the axions that, yeah, that's true.
There's no dependence of axion coupling to matter, right?
For this one.
Yeah, so there's no solely purely gravitational.
Yeah, the simulations are purely gravitational. Yes, yeah.
Otherwise, if you have some differences of axion coupling to the matter,
Yeah, in that case, it would have been specific. Okay, yeah.
So that's what
Okay, yeah, so yeah, I think the simulations are mostly gravitational, right? Yeah.
This is E-only simulation, right?
Sorry?
This is only a E-only simulation, or baryons are present?
I don't think baryons are present for this simulation. But
Well, here the stars, we should have somewhere something.
Yeah, for the hardness you will need two type of particles.
For that is physical applications.
okay, so we do look at the interaction between a single mini-halo and a single star, but we also look at successive stellar encounters where we taken a single mini-halo, we taken say an unperturbed NFW mini-halo, we subject it to a stellar interaction, we let the remnant mini-halo from that stellar encounter relax to a Hernquist density profile mini-halo, and that's the first generation mini-halo, and we subject that first generation mini-halo to another stellar encounter, and we let the remnant mini-halo from that encounter again relax to another Hernquist density profile mini-halo, and that's the second generation, and we keep on going like that. So this is the scenario we are considering. So more concretely, if you are given the concentration parameter C sub s of the unperturbed NFW profile mini-halo, and we subject it to stellar encounters, each with energy injection parameters E sub frac comma s, E sub frac comma 1, E sub frac comma 2. So how the energy injection parameter is defined is it's a single parameter ascribed to the stellar encounter, and is defined as the ratio of the energy injected into the mini-halo to the binding energy of the mini-halo. And during this multiple stellar encounters, we allow the mini-halo to gravitationally relax in between those encounters.
What is
C? C is the concentration parameter, and it's defined as the ratio of the virial radius to the scale radius. Okay, and we want to ask the question, can we predict the mass loss or the cumulative mass loss at intermediate points, that is in between those stellar interactions, and those come out from these quantities. And we quantify mass loss by a quantity called the survival fraction S dot F, wherein S dot survival fraction is defined as the mass of the mini-halo that survives immediately after stellar encounter to the mass of the mini-halo that was there immediately before the stellar encounter. Okay, and here are the results. On the horizontal axis is the energy injection parameter, and on the vertical axis is the survival fraction, and it just put in a slightly more mathematical form here. The blue solid line is the single encounter case, whereas I'll only talk about the green curves for now. So the green solid line with circular markers is the output of a analytical procedure, wherein each one, so these are multiple stellar encounters, and we see how the survival fraction keeps decreasing, and for this case each of this energy injection parameters is equal to 0.1. Now there was this paper by Shen et al, which will abbreviate as S2024, that did numerical simulation. So they did n-body simulations for a similar scenario, and their result is in the dashed line with the triangular markers, and there's a fair degree of agreement between our analytical calculations and their numerical simulations.
So, one question. So, what is the time scale of this? So, when this stellar encounters happens and this halo decreases its concentration parameter, so what is the time scale associated with it?
Are you talking the time between the stellar encounters?
Yes, yes.
For the purpose, this is just the initial calculations that we did. The purpose of these calculations, we assume there's an infinite time. So that in a sense, like it completely after the stellar encounter, the mini-halo completely gravitationally relaxes before a second stellar encounter is applied.
Because this would have an impact on the halo mass function, right? So, what halos are abundant at what redshift, something like that?
I'll come to the halo mass function a little later. So when we look at a galactic population of mini-halos, so far this part is mainly just like one mini-halo interacting with one star, but we do it multiple times for the same minihalo.
So there are papers like from Malcolm Fairbairn and these people, so they say that there would not be so many these encounters so that the axion minihalo would not disrupt and you won't get sort of flux of axion to your direct detection studies. So these people sort of argue in these slides. So what is the sort of probability of these encounters that axion minihalo disrupt?
A little shortly ahead, we'll look at a galactic population of minihalos. So when a minihalo orbits around the galactic center, it will cross the stellar disk, and it depends on the time period of revolution. So every time it crosses the stellar disk, it should technically undergo some disruption, because these minihalos tend to be of mass, maybe 10 power minus 7 solar masses. So there's a huge density of stars in the stellar disk, so there will be some disruption when it undergoes.
Sorry, why this E fraction is considered to be 0.1 and E1 is like 7.8? 7.8 is a big fraction.
So the reason we chose these values were the numerical simulations actually chose those values, and we were free to choose any values we wanted just to demonstrate we were free to choose any values within the analytical model. However, to make sure our analytical predictions matched the numerical simulations, we took the values that the numerical simulations did. And yeah. Okay, now just a brief into adiabatic versus isocurvature perturbations, and I hope I got this right. This is a new slide. We look at the early universe, and we can imagine just for now a one-dimensional universe with the spatial dimension as x, and we look at the number density of a certain particle species, and it's a function of x, and it varies along the with the spatial dimension. That's the blue curve over here, and what I can do is I can average the density variation over space to get this orange line, and that's called n bar. So that's the mean density over all space, and that does not have a specific spatial dependence because we averaged out the spatial dimension. So now we can define a quantity called delta n of x, which is defined at any point in space. So you take the number density at that point in space and subtract the mean number density. So that's called the density perturbation at a point in space. And for adiabatic perturbations, if you take this term delta n by n bar, which will be a function of space because delta n is a function of space, if there are multiple particle species undergoing adiabatic perturbations, this term delta n by n bar will remain equal for both of them. For all of them as a function of space. On the other hand, if you're talking about isocurvature, that's the other extreme case, this equality doesn't hold true, so there will be a not equal to sign. And in some gauges, you can this condition becomes true, wherein delta rho is the perturbation in the energy density and is defined in a similar way as this guy. And if you look at the density perturbation for different particle species and sum them all up, that should equal 0. Is that right? Let's talk about the mass function of minihalos. It turns out that the minihalos are formed from collapse of isocurvature density perturbations, not of the adiabatic density perturbations. And there was a code in Python called the code for anisotropies in the microwave background, which I'll abbreviate as CAMP, which allows us to calculate the isocurvature growth function. Now, the isocurvature growth function tells us how the isocurvature density perturbations of the axions evolve with time. There is a semi-analytical tool called the Shed-Torman formalism, which allows us to calculate the mass function of minihalos. It's a semi-analytical tool. So in very crude terms, it basically takes the initial axion density perturbations and it smooths it with a spherical top hat filter of a given length scale, and the length scale of the spherical top hat filter is dependent on the mass of the minihalo considered. Now, there was a paper by Zhao et al. Which I abbreviated as X 2021, and that performed numerical simulations to find out the mass function of minihalos. And what they did was they took the Shed-Torman formalism, which has 3 parameters of some given values, and the parameter fitted these 3 parameters to the output of their numerical simulation. And it's difficult to keep doing the numerical simulation for multiple different cases. So what happens with the parameter fitted Shed-Torman formalism is you now have a semi-analytical tool to apply it to different cases, and we use this modified Shed-Torman formalism to generate the mass function of minihalos.
So there are constraints on isocurvature perturbations from the CMB.
From the CMB, is it?
From the CMB. At what level are these?
I don't know.
It's adiabatic and there's a little bit of constraint on isocurvature.
I don't know much about the CMB, but I know for the I think the curve, if you look at the matter power spectrum, as far as I know, so the adiabatic perturbations curve like this, and this is with K, right? And there's a spike here and the spike corresponds to the isocurvature perturbations. It,
So CME has first few foldings of inflation. So power at very large scale is tested. So that is just around the peak. So after the small peak, it's not tested at all. So you have a lot of freedom for any sort of perturbations you can enjoy. So it's not a delta function, but it flattens.
you may flatten Slada?
Like flat.
Just flat, okay.
So you are just high power. Yeah. So if you have perturbations at small scales, isocurvature, then make such features.
Okay, okay.
So it also depends on the power you put in, but roughly it's like that. It doesn't form as mass.
Yeah. So the isocurvature perturbations do happen on a smaller length scale, I think, compared to the adiabatic. And this adiabatic, when the adiabatic perturbations they collapse, they generally host galaxies. I mean, that's a kind of scale of the adiabatic perturbations.
Whereas isocurvature hosts smaller structures.
Yeah, and we call them minihalos. Yeah.
And the delta function probably corresponds to like a monochromatic mass.
I'm not very sure. I mean, I remember discussing this with my supervisor.
It can never be local. It's always some high power.
You, let's say you put a delta function in the primordial power spectrum.
Yes.
But in linear perturbation theory, when you find the resolution, it all smoothens out, right? Smoothens out something.
Okay. Okay.
But CMB has constraints on isocurvature, right?
Yeah, they're very poor.
Poor constraints.
So at small scales, perturbations of the order 10 to the minus 1 is still allowed.
Okay.
But at large scales, like at gigaparsec scales, perturbations of the order 10 to the minus 9 is constrained.
Okay. That's what. Thanks.
So looking at the adiabatic perturbations, the adiabatic perturbations of axion density, they occur on significantly larger length scales than the isocurvature perturbations. And when these adiabatic perturbations collapse, they form what are known as adiabatic halos. And these adiabatic halos are large enough to be host to galaxies. Now we quantify this, there's a term that we can quantify, it's called the collapse fraction. And it's a function of redshift. And what we say is that, so the collapse fraction is defined as that fraction of the total axions that participate in the adiabatic perturbations that are collapsed to form halos by a certain redshift. The adiabatic halos, they generally form much later, and as far as I know, it's probably around earlier than z equals 100, whereas the minihalos, they form significantly the adiabatic portion form much later, and the isocurvature perturbations that give rise to minihalos, they form at around more around the matter radiation equality. When the adiabatic halos do form, the minihalos are already present in a region and they consume the minihalos. And the technical term for this is the minihalos have fallen into the adiabatic halos. And when this happens, the properties of the minihalos freeze, and that's because further merging of the minihalos is prevented inside the adiabatic halo due to high virial velocities in the adiabatic halo. To compute the collapse fraction, we first use the CAM code, and there's a formalism called Press-Schechter formalism, which is very similar to the Shed-Torman formalism. And the CAM code does this internally for us. So we use the Press-Schechter formalism to first compute the mass function of adiabatic halos. And after we get the mass function, we integrate the mass function over relevant mass range to get the collapse fraction of adiabatic halos. So far, what we've done was when I talked about this when I talked about this mass function of minihalos, we actually called the pre-infall mass function. And this pre-infall mass function evolves regardless of whether the adiabatic halos are formed or not. But now we want to ask the question, what about the mass function of minihalos inside adiabatic halos? And to do that, we perform this integral. So we first take the mass function of minihalos, that's over here, and we multiply it with the derivative of the collapse fraction of adiabatic halos with respect to redshift, and we integrate that over all relevant redshifts that we have. And we start off with Z sub equality because the minihalos start forming around then, and we can take it up to any redshift that we want. But usually we say we are looking at the minihalos today, so we say this value of Z equals 0. So this gives us the final mass function, and this final mass function is basically the mass function of minihalos inside adiabatic halos. And so this part is the isocurvature part, and this part is the adiabatic part. Now we wanted to look at, now so far we mainly considered how a single minihalo may interact with a single star, but we wanted to consider how a galactic population of minihalos interacts with the stellar disk of the galaxy. This is a bit more challenging because we're looking at structures of very different length scales. The minihalos probably have a virial radius of 0.01 parsec, whereas the entire galaxy is much bigger. So what we first do is we start drawing orbits of minihalos randomly, and we need to draw it from some underlying density distribution of the minihalos within the galaxy. So we assume that the minihalos in the galaxy are distributed according to the density profile of a singular isothermal sphere. In reality, this is not exactly true. We expect it to be distributed according to the NFW profile. However, during the process of generating orbits from this density, we have to consider the phase space distribution function, and we need an analytical phase space distribution function. And it turns out that the NFW profile doesn't have a well-defined analytical phase space distribution function, whereas the singular isothermal sphere does. So this is kind of the next best thing we can do. So the singular isothermal sphere is given by this density profile, and it falls off as 1 over r square. V sub c is the circular velocity. This means that if a minihalo is on a circular orbit around the galactic center, no matter what radius the orbit has, the speed of the minihalo is always v sub c. Okay, so now we use the Monte Carlo procedure from a paper by Van den Bosch et al. To randomly draw orbits from the singular isothermal sphere, and out of the procedure also tells us what the energy and angular momentum associated with the orbit is. Now during the procedure, we fixed the minihalo's position today to be the solar neighborhood. So this determines the initial position vector. And we use the energy and angular momentum of the orbit to determine the velocity vector of the minihalo today. Now,
One second. So, just to be clear, inside a minihalo, you are assuming an
Uh,
becomes the 1 over r cubed thing, right?
No, this is kind of like the distribution of mini-halos within the galaxy.
I understand. Yeah. This is the distribution of minihalos within the galaxy, but inside a minihalo, you are assuming NFW. Is it or how?
Inside the mini-halo, if it's unperturbed, if it's not stellar disrupted, it's NFW.
Okay.
If it does,
After stellar disruption, it becomes Hurmquist.
it becomes close to a Hurmquist, yes.
I ask because aren't these at odds with each other, these two assumptions? Because if you want NFW, if you want inside a minihalo to be NFW, presumably it means there's a hierarchical structure formation that goes into the n-body simulations, and you make it NFW. Shouldn't the same logic apply to a larger scale also? And shouldn't the galactic halos also be assumed NFW?
Oh yeah, actually the galactic halo, are you saying that the...
so instead of this isothermal, shouldn't this also be NFW?
Yeah, that's what it actually should be NFW, and but the only problem is like the while drawing random orbits from the NFW profile, we needed to have a analytical form for the phase space distribution function, and it's not,
Okay.
and we can't have that for the NFW. So this is the next sort of best thing that we have,
Okay.
and that was the reason we adopted the singular.
Inversion you want to do.
Sorry.
You want to do some editor inversion to get the actual phase space.
Yeah, I think there's an editor inversion formula.
Actually, let's see.
Yeah, the isotherm. Yeah, this at least has a analytical form for the phase space distribution function. So that was the next best thing we could apply.
Okay. Okay, sure.
Okay.
Sorry, I have a nice question. So why you are considering axion is basically form a minihalo, right? Other properties of axions are not needed for your.
Okay.
So why are you saying this axion is my question? These halos. To form minihalos is why you require axions or any other properties of axions are utilized?
Okay, to form, so the thing is like there is an aspect of how the axions are formed in the first place. It's called the breaking of the Peccei-Quinn symmetry. And if this Peccei-Quinn symmetry is broken after inflation, that's the only case where we get the mini-halos.
So the formation of minihalos is required for this axial consideration, none other than that. Because everything other than that is gravitational minihalos. No other interactions of axions is not.
Yeah, in our computation, we don't consider any quantum effects. Like yeah. Oh, this one. I mean, I would wonder if it has something to do with the galactic rotation curves, but I'm not sure.
So in general, it's a function of R, but it flattens out after large.
Oh no, the thing is like, so this is just the density profile viewed on larger scales. But on shorter scales, the you'll get like variations, and the mini halos can be on a elliptical orbit or a circular orbit. It's only when it has a circular orbit it has the speed of v sub c.
Sure, but the V sub C itself in general could be a function of R.
Oh, we do not assume it to be. Well, okay. There is, I think. Yeah, we do not assume the
That's
dependent.
still fine,
Yeah.
because it flattens out
Okay.
for most things. Not only side, exactly.
For the circular orbits, you consider it same. I don't know. For the small parts, can we say the orbits are circular?
That is beyond the core radius, I guess. Beyond the core radius, you can assume
It's
You
flat.
know, co-radius is not circular.
the potential is constant beyond the core radius because all of the mass are concentrated within the core of that.
The potential here for the singular isothermal spheres, I think log r. It goes in log r. But we assume this is at least for the purpose of the singular isothermal sphere, it's slightly scale free, as in like it falls off as 1 over r no matter what. But that's obviously a bit of an assumption. Like maybe at very small radiuses you can't have that. Okay. Um, where have we reached? Okay. Okay, so now we've been able to calculate the initial position vector and the initial velocity vector of the minihalo today. And now we have to evolve the minihalo trajectory backward in time. So there is a code called LB particles which was developed by my collaborator Dr. John Forbes. This is a Python implementation of an epicyclic orbit solver which was initially proposed by Lyndon Bell in his 2015 paper and is applicable for bound orbits in a spherically symmetric potential. Now the state of a minihalo is given by its position vector and its velocity vector, and given the initial state of the minihalo and a known galactic potential, the LB particles derives a set of coefficients that can be used to evaluate the minihalo state at any arbitrary time into the past or in the future.
What is epicyclic orbit?
So there are so epicyclic technically means like there's a rotation in the so I think what John said was there will be a certain radial oscillations like when you actually do the trajectory evolution, and that kind of I think refers to the epicyclic behavior. Okay, now.
Some minihalos have even smaller minihalos orbiting them rather than the.
No, it's not really that. As you said, it's the radial perturbations, orbital perturbations.
The motion of the moon from the sun.
That would be like a true epicycle, but this is like you take a circular orbit and then you have some radial perturbations.
There'll be some radial oscillations.
Every object does that.
Okay, so now this is the main workhorse of our computation, which is initially proposed by the S2024 paper. We initially created two-dimensional grid of, so the two-dimensional grid on one axis we have the minihalo mass values, and on the other axis we have the infall redshift values. You can think of it like a matrix, if you will. And each entry is called a grid point. And to each grid point we assign a single minihalo orbit, and using that minihalo orbit we compute the mass loss in the minihalo due to stellar interactions, which I'll come to shortly how we do that. And to each grid point we assign what is known as a weight, and the weight will be a function of m and zi because each grid point has its own mass and infall redshift. So this weight is given by this term, and this term looks familiar because it is actually this term but in a discrete form. It basically counts the number of minihalos that have fallen into the adiabatic halo during this delta zi redshift interval. Okay. Okay, now the minihalos are more or less distributed isotropically in the galaxy, whereas the stars in the galaxy are more or less relegated to disk. And when the minihalos orbit the galaxy, they pass in and out of the disk, and as the minihalo passes through the disk, we call that a single disk pass. And the energy injection parameter E sub frac corresponding to a single disk pass is given by this expression. It was recently published in a paper by another paper, S2024. So I won't go into the details, but our contribution was to more accurately predict this term, sigma star, which is the stellar surface density for a single disk pass. And the way we calculate it is we first model the Milky Way stars, or the stellar density in the Milky Way, which is given by rho star, which is the stellar volume density. And it's modeled in cylindrical coordinates r, z, and the stellar volume density falls off exponentially in the radial direction along the plane of the disk, and also in the z direction perpendicular to the plane of the disk. And we do the contribution, we consider the contributions for both the thin disk and the thick disk. So now we take the stellar volume density over here, and we integrate that along a single length dimension along the trajectory of the minihalo to get the stellar surface density. And all I've done here is converted dl to v dt, where t is time and v is the instantaneous speed. So now I have a sample orbit here, wherein on the time is on the horizontal axis, and this integrand rho star v is on the vertical axis. The circular red markers are the local maxima, and these correspond to the instances where the minihalo passes to the stellar disk, that is at z equals 0. On the other hand, the orange diamond markers, these are the local minima, and these correspond to the instances where the minihalo is effectively furthest away from a disk pass. And we assume one disk pass as from one local minimum to the next local minimum with the local maximum in between. And so that's the domain of this traj over here. So if that's how we get the stellar surface density for a single disk pass. And then we go back here and insert it in here to get the energy injection parameter for one single disk pass. Now the question is, the minihalos during the life.
Sorry, I'm trying to understand that plot again. So first of all, it's periodic, and then every time you have a disk pass, there's a probability of encountering stars, and you might either encounter it really close by or somewhat farther away. If you're close by, then it corresponds to one of those high red points.
Yeah.
And if it's a little farther away.
Yeah, that would be because most of the orbits are elliptical, and also there's a precession of the orbit in the plane of the orbit. So you could, so you could. It enters at different radii, and that's the reason some of these circular dots are higher and lower. That again, it depends on so I mean, if this is the disk, right, it depends on whether the so this would probably be one minima, but this would also be another minima. So they could be at different distances from the disk, and therefore the minima also vary. Are you talking about this point here as opposed to these? Okay, yeah. We assume that, while drawing the minihalo orbits, right, we assume that the position of the minihalo, initial position of the minihalo is in the solar neighborhood, which is in the stellar disk. That's why it starts off as a maximum. Okay, now the minihalo orbits the galactic. So the minihalos in the galaxy orbit the galactic center and pass through the stellar disk multiple number of times during its lifetime. And we want to add up the energy injection parameters for each of the single disk passes. And there was a paper by Stucker et al. That proposed a formula for the energy to calculate the effective energy injection parameter for multiple disk passes. And this is the expression. So where E sub frac comma I is the ith energy injection parameter for the ith disk pass, and E sub frac comma EFF is the effective energy injection parameter, and P is some number to be determined, some dimensionless number. Now the S2024 paper assumed P was equal to 2, and if P equals 2, this is just a linear sum. But in doing so, what they did not take into account is the density profile changes that can occur in the minihalo in between disk passes. And these density profile changes are mainly because of the gravitational relaxation of the minihalo if it has enough time to do so. And we found that if the minihalo does have enough time for relaxation in between disk passes, the value of P is closer to 1. Now, when P is equal to 2, this is a simple linear sum. But if you decrease the value of P from 2, for fixed E frac comma I, the effective energy injection parameter becomes more. If the effective energy injection parameters become more, the mass loss in the minihalo becomes more. Thus, when we consider the gravitational relaxation effects, the effective mass loss in the minihalo becomes more. And a similarly qualitative result was reported by Delos in his 2019 paper. Okay, now comes the question whether we want to add up the energy injection parameters with P equals 1 or with P equals 2. To do this, we first need to figure out the time scale for the gravitational relaxation, and that we call it the dynamical time, T sub dyne, and is given by this expression right here, where rho bar where is the virial density of the minihalo at its infall redshift. And so now we take two consecutive disk passes. If the time between those two consecutive disk passes is less than the dynamical time of the minihalo, we say that the minihalo doesn't have enough time to relax in between those disk passes, and that the energy injection parameters should be added up linearly with p equals 2. And this is the expression here. On the other hand, if the time between consecutive disk passes is greater than the dynamical time of the minihalo, we say that the minihalo does have time to gravitationally relax in between the disk passes, and the energy injection parameters should be added non-linearly with p equals 1. And this is the expression right here. So we look at all the multiple disk passes and we do the appropriate addition with p equals 1 or p equals 2. And so we call this sort of like a hybrid p method. And we calculate the effective energy injection parameter for all the multiple disk passes during the lifetime of the minihalo in the galaxy. And once we know that, we can treat it as a single encounter case, wherein we know the initial concentration of the unperturbed NFW minihalo, and we know the energy injection parameter, and we can get the survival fraction.
So E is equal to 1 when the minihalo can relax between two collisions with this disk. Why is there more energy injection in this case?
Okay, I can, so obviously that comes out of the mathematics, but I can give you P. Okay. So one thing I can say is like what happens physically is so you have a minihalo of a certain distance, and we kind of like for our initial calculations do it. We assume it's at infinity. But what happens is when there is energy injection, there is a radius called the crossover radius. I can call that R star. So beyond this crossover radius, all mass is lost. All mass in the minihalo is lost, and this remnant minihalo now relaxes. Now if I don't let it relax, I apply two stellar interactions. In both the stellar interactions, mass beyond this radius is lost. But if I do allow it to relax, now this part becomes big. And then when a second time I do the stellar interaction, again mass beyond this is lost. Larger fraction is lost when you allow it to relax. So that's kind of like the physical intuition for it.
So whether it will be the first case or the second case should depend on the redshift, because at some redshifts are not. So I mean, when do you consider the first case and when do you consider the second case?
Okay, so we consider, the first case, we just look at the time between consecutive disk passes, and we treat each disk pass as maybe like a single encounter, a single stellar encounter, and if it has time to relax between those two stellar encounters, we assume p equals 1. And in order to figure out if it has time to relax, we had to compare it to the dynamical time scale of relaxation. So
You consider two different cases separately and then you run simulations.
No, so the LB particles code, it gives us a position history of the minihalo. So we know what are the, so once we run it over the whole lifetime of the minihalo, we know what are the time between each consecutive disk passes. And then we start looking from the left side, say, and we say, is there enough time for relaxation? Do we need to add them with p equals 1 or 2? And then we keep going through the array. Can you say that again?
So the QCD axion potential, sinusoidal potential, cosine potential. You can have a quartic coupling that mediates 4 axions. Contact 4 axion interaction. Roughly goes as F pi over F8.
Okay, okay.
So this induces self-interaction on top of gravity. That's what I mean.
Oh yeah, we do not consider, we haven't considered that.
But
Yeah.
then, because it's a series expansion, changes sign as a function of field value. So I think the situation is a little more involved than this, unless you show that the field value is always small
Okay.
inside the mini cluster or whatever.
If the
Okay.
demonstration is considered to be very high, then probably can be because it is A over everything. Cost of Fi over
Fi over Fa.
yeah, Fi is constant. Fi is constant.
No, sure, whatever it is, even if it's small,
Yeah, it
if
can
you
be
do the observation number is large, it becomes all one. So, just a remark.
Okay, yeah, we haven't considered non-gravitational couplings on this, yeah. Okay, now we want to calculate the mass function. And we look at two different cases. So one is without incorporating the effects of stellar disruption, and in the second case, incorporating the effects of stellar disruption. To compute the undisrupted mass function, or without incorporating stellar disruption, we take these weights which were assigned to each grid point in that two-dimensional grid of mass and infall redshift, and we bin them. We use mass bins, and we just bin them. When we bin them, we don't just if a weight falls in a certain bin, we don't just count it as 1, but we count it as the value of the weight. The magnitude of the weight gets inserted there. And basically what this does is it actually performs this integration. Doing this mass binning, it actually performs the integration along the z-axis. Okay, so that's how we get the undisrupted mass function. Now, what about the stellar disrupted mass function? We had figured out how to get the effective energy injection parameter for each orbit in that grid point, and then we were able to calculate the survival fraction due to that. So now we need to know what's the final mass in each of those grid points. Where m is the initial mass, if we multiply that with the survival fraction, we get the final mass. And now that m gets replaced by m sub f, and now we do the binning again, and the mass spins that we consider were the same mass spins as the original undisrupted mass function. And so say if m sub f falls between a bin of bin edges m sub I and m sub I plus 1, we insert the weight in that bin, and we count not just 1 but the value of the weight itself, and that gives us the stellar disrupted mass function. And here are the results, where original represents the original represents the stellar undisrupted mass function, and survive represents the stellar disrupted mass function. And the mass function here is a slightly different form than the regular dn by dm version, and on the horizontal axis is the mass. So few things we can see from this is that firstly the undisrupted mass function gets suppressed. This is due to mass loss occurring due to stellar disruption. The second thing we can see is that the peak of the stellar mass disrupted function over here has shifted towards the left, towards smaller mass values. This again is a sign of mass loss from the minihalos. And the last thing we can see is that the stellar disrupted mass function is noisy. The reason it's noisy is because we used a Monte Carlo procedure wherein at each grid point we have assigned a randomly generated orbit, and each randomly generated orbit will have a different energy and angular momentum. So that's the reason for this noise. And when we run it multiple times, the simulation, the exact value of this noise takes will be different, but there's always a semblance of the general curve. And our final result is insensitive to this noise. To find the we have the mass function in the previous slide. We want to find the mass in minihalos in the Milky Way galaxy. To do that, we take the mass function in the dn by dm form. So this is the number density of minihalos per unit mass interval. We multiply that by m. So that gives us the mass density in minihalos per unit mass interval, and we integrate that over the relevant mass range to get the mass in minihalos. So we do this in two cases. One by considering the undisrupted mass function. In that case, we get the mass in minihalos that originally fell into the galaxy, but we haven't yet considered the effects of stellar disruption. And when we take the stellar disrupted mass function, we get m sub survive, which is the mass and mini-halos after incorporating the effects of stellar disruption, and we divide the two. So m survive by m original basically tells us in terms of mass what fraction of the mini-halos that have originally fallen into the galaxy survived till today. And the S 2024 paper found this value to be 58%, but they did not do a full Monte Carlo simulation. They did partly Monte Carlo and partly they used probability density functions to generate correction factors. But we evolved our orbits of the mini-halos to get a more accurate answer, and our answer was 30%. So we found that more mass is lost in mini-halos than what was previously estimated. And where does this mass go? It does not exit the galaxy, at least we don't think it exits the galaxy. It goes into the inter-mini-halo voids, the inter-mini-halo space, which we call as mini-voids. And we expect the Earth not to be inside a mini-halo, but inside one of these mini-voids. So what did you say about the escape?
You said you thought that the disrupted free axions don't leave the galaxy, but you can just check this by seeing what the
Escape
speed
velocity.
of the recoiling axions are.
But I wonder if you can get that without numerical simulations, like.
On an average, so from your formalism, on an average you can get, because you have fraction energy losses in the
Okay.
just for momentum energy conservation, should you just get what is the speed of the broken out parts are?
But I think the way this mass loss is incorporated here is more like a recipe. If this much is the injection, then outside this radius things are mixed or not with the details that you will need for the distribution of the velocity.
But which fraction of mass is lost? If we equate it with the total energy injection, we kind of know the velocity of this.
Statistically.
Okay.
Anyway.
Okay. Yeah. So what this does is we expect that if in such a case where more mass is disrupted, the local axion density at the Earth would increase, and the chances for direct dark matter detection would relatively be higher by Earth-based experiments. And now I've given the same. Here's a graph. I have the same fraction m sub I by m sub original, but I've evaluated it for different axion masses, and there isn't a huge dependence on axion masses. And I only look at the diamond. I only look at the diamond markers for now. And the method that we described with the p equals hybrid, which is either p equals 1 or p equals 2, is this case. But had we only done p equals 2, which is what effectively the S 2024 paper did, we would get this case. So we are incorporating the gravitational relaxation of the mini-halos. We actually find that more mass has been disrupted, and this just showcases that again. Now, in conclusion, we improved upon the Kavanagh et al. K 2021 analytical model by introducing a sequential stripping model and also mini-halo relaxation. We also explored successive stellar encounters and found that the mass loss is more severe than simply adding up the energy injection under the case that enough time for mini-halo relaxation is available. We also developed a new code to evolve the mini-halo trajectories, and we compared the time between consecutive disk passes to the dynamical time of the mini-halo to more accurately predict the effective energy injection parameter. And finally, we found that the percentage of mini-halo mass loss that survives today is significantly smaller than that reported in the literature. Yeah, that was my talk. Yeah.
So, at which redshift you started your calculation? My concern is within the how many orbits you have taken, and if within the total time scale, the total structure of these galaxies are not altered.
Yeah, we've assumed a static model for the galaxy.
Yeah, but the galaxy is not
Not in our model, no, no. But yeah, I mean, the infall redshifts we consider in this are till 150.
150.
Yeah, 150 Z, yeah. And we assume, I mean, it's possible to have a dynamical model for the galaxy. I mean, but we didn't do that yet. No, no.
So I don't know, here at Z150 the galaxies are in the same shape.
It's not there. You will not definitely start this and all.
Yeah, that is what I know.
Did Bradley Kavanaugh do that?
The
The dynamical relaxation of galaxies from
no, actually he did not.
Did only Milky Way?
Sorry.
Did he do only Milky Way?
He did some procedure for the Milky Way, but so those numerical simulations I've talked about, his output did not exactly match the numerical simulations in the first place, and they only matched the numerical simulations supposedly at C equals 100, the concentration C equals 100. But when you change that from C equals 100, it no longer matches. So I don't know how accurate his results would be, but he did not evolve the trajectories like we did, and he did not consider gravitational relaxation in between trajectories.
Can you go to the
Previous
previous part?
slide.
Yeah, how to understand this dependence, this MA and the survival dependence? So the dependence is pretty weak, right?
It is pretty weak for a couple of orders of magnitude.
Yes, but still it's falling, right?
Yeah, I don't know. So it is a little complex, the relation, because it comes in two places. One is like, so you remember the two-dimensional grid of mass and infall redshift. Corresponding to that, for different minihalos, slightly different concentration gets ascribed to that grid point. So there one dependence comes, and the second dependence comes in the mass function of the, when you're generating the mass function of the minihalos itself. A little different minihalo, little different axion mass will generate a little different mass function for the minihalos. So and that is a little more complicated equation, so it's difficult to say exactly why it falls, but there are dependencies. But when we find that the dependency on the axion mass is not too high.
So for the collapse of the minihalos, you considered shape tone formalism.
Yeah.
And for the idealic, you considered mesh vector.
Yes.
So is it related to the fact that it's isocurvature and it's idealic?
The reason, no, actually the Shed-Thurman formalism technically is more accurate, but the reason we considered minihalo mass, this was a while back, but those perturbation, they go on a white noise matter spectrum for the isocurvature case, and there is a very easy formula for applying the Shed-Thurman formalism and the analytical form. Whereas in the Peccei-Quinn form with adiabatic halos, we let the CAM code do it for us, and there is no analytical form, easy analytical form for us to do that. And the CAM I don't think handles, it might handle Shed-Thurman, but we did it with the Peccei-Quinn case. Partly because the paper we worked with, I mean the paper one we had cited before did the same thing, and we wanted to just compare our results to them. That was kind of the main motivation for the adiabatic having the Peccei-Quinn.
So this major change that you see, 58% versus 30% with the earlier result, that primarily comes for your choice of T, that the way you argued that T will be 2, not 2, but more close to 1, like it changed from 2 to 1. Is that the reason?
So that is one of the reasons where if you always consider P equals 2, you're not considering gravitational relaxation in between the disk passes, but there is a potential for considering it with P equals 1 or P equals 2, so that's a hybrid case. So that's one of the reasons it decreases, because you incorporate some of those energy injections for disk passes get added up with P equals 1, causing more energy injection. So that's one of the reasons that curve comes down. Another one was even this. So this is still not 58% if you notice, like from the previous estimates, and that was kind of also because the previous estimates, they did not do a full Monte Carlo simulation. They used probability density functions for the sigma star, the stellar surface density. They determined an average stellar surface density, an average angle of incidence for the disk pass, and they did so there is some discrepancy between our and their formula, procedure. But we think our procedure is a little more accurate than just developing PDFs for determining correction factors.
And then there is also significant change based on your the minimum kilomass, that 10 power minus 2 and 100 that is considered.
Yeah.
But in your previous slide, you also have some numbers like 10 power minus 12.
Oh, so
That number, what is that?
no, so this Mn is actually the minimum mass of the adiabatic halo, and the reason we considered 2 was again we wanted to compare our procedure to one of the previous papers, the output of one of the previous papers, and they said that they used 10 power minus 2, and we were not able to reproduce the graph for the collapse fraction of adiabatic halos. Then when we interacted with the researcher, we found out that in code they actually used 10 power 2 instead of 10 power minus 2. So we did it for both the cases, and the 10 power 2 is what they really used, and to compare our results to theirs, it should be the 10 power 2 case. But ultimately what we want is that the minimum mass of the adiabatic halo should be at least greater than the maximum mass of the minihalos considered. And the maximum mass of the minihalos we consider 10 power minus 3 solar masses.
Sorry, but when does this when does that coefficient calculation?
Where does that change?
Yeah, I mean, where is it coming in the calculation?
Oh, where is it coming? Okay. Yeah, so here, so we use in the CAM, right, we use the Peccei-Quinn formalism to get the mass function. So the range of the masses that mass function is evaluated for changes the collapse fraction. So if the lower bound is 10 power minus 2 solar masses versus 10 power 2, you get a different value for the collapse fraction. And if you get a different value for the collapse fraction, this term changes.
And the 10 power minus 12 is when you integrate that dn equation for your the minimum of that. Right?
Yeah. So we integrated from actually 10 power minus 12 to 10 power minus 3 really, but we don't haven't seen, and this is the minihalo case rather than the adiabatic. Yeah, that's why this has a greater than 10 power minus 12.
Okay, let's thank the speaker again. So Ian will be here tomorrow as well. And by the way, tomorrow we have another talk at 2:30 DSouza.